Hello, so this is a revision video for AP Chemistry 3.5, Kinetic Molecular Theory. This is a revision video, so only the essential information is covered. For more detailed explanations and full video lessons, please check the links in the description below. Kinetic Molecular Theory, or KMT, provides a particle-level model for understanding the macroscopic properties of gases, like pressure, volume, and temperature, based upon how the particles in the substance are moving and the energy that they have. There are several core assumptions of kinetic molecular theory, rather like for ideal gases. Gas particles are in constant random motion. Volume of an individual particle is negligible. There are no intermolecular forces between particles, so no attraction or repulsive forces. Collisions between gas particles and their container walls are perfectly elastic. No energy is lost or gained, and the average kinetic energy of gas particles depends only on temperature, in Kelvin. Central to kinetic molecular theory is the idea that temperature is used as a measure of the average kinetic energy of particles in a substance. So when something feels hot, its particles are moving faster than when it feels colder. Kinetic energy increases as temperature increases. At absolute zero Kelvin, particle motion stops completely. This is the theoretical lowest temperature possible. The motion of gas particles is related to average kinetic energy, and so temperature, by the equation Ke equals half mv squared, where Ke equals kinetic energy in joules, m equals the mass of particle in kilograms, and v equals the velocity of the particle in meters per second. This shows us that at a given temperature, so a same average kinetic energy, lighter particles are going to move faster and have a higher velocity, and heavier particles are going to move slower, a lower velocity. Exam tip here: don't confuse speed or velocity with kinetic energy. Different gases at the same temperature have the same average kinetic energy, but different velocities because they have different masses. Kelvin is the SI unit of temperature used in science. It has the same step size as degrees Celsius, but the Kelvin temperature scale starts at 0 Kelvin, absolute zero, and 0 Kelvin is the same as minus 273 degrees Celsius. Meaning, to convert degrees Celsius to Kelvin, we have to add 273, and to convert Kelvin to degrees Celsius, we have to subtract 273. The reason we use a Kelvin temperature scale is because it is directly proportional to the average kinetic energy of particles in a substance, whereas degrees Celsius isn't. Maxwell-Boltzmann distribution curves are graphs that show the distribution of kinetic energy in a gas sample at a given temperature. What these distributions show us is that at any one moment in time, gas particles in a sample can have very different energies, with some moving much faster than others. The most probable energy that molecules have is given by the highest point on the curve. And the curve is asymmetrical and never actually touches the x-axis again, telling us that at any one moment in time, a very small number of particles can have a very large amount of energy. As the temperature increases, the peak of a Maxwell-Boltzmann distribution curve flattens and shifts to the right. This is because particles are moving faster on average because there's a temperature increase, so the distribution becomes wider. More particles are likely to have a higher amount of energy than before. Gas pressure results from collisions between gas particles and the walls of the container they are in. The more frequent or more energetic the collisions, the higher the pressure of the gas. If you increase the temperature of the system, because the gas particles are colliding more frequently and with greater energy, the pressure will increase. Equally, if you increase the volume of a gas at a particular temperature, the particles will have the same amount of energy but will collide with the walls of the container less frequently because they're in a larger volume, meaning a lower pressure overall. Exam tip here: on questions involving kinetic energy and temperature, always convert your temperature to Kelvin from degrees Celsius. For Maxwell-Boltzmann distribution curves, remember a higher temperature means a lower but wider peak that's shifted slightly to the right.